Back in chapter 11, we started talking about standing waves. Now we're going to go through standing waves in a little more detail. In our last video talking about pitch, we ended talking about the standing waves inside of a tube. Well, we'll come back to that in just a second. But just as a reminder, these were standing waves that we saw in chapter 11 in a string. What we saw was the string would vibrate. If you have one antinode in the middle, then that's your fundamental frequency, n equals 1, which has a wavelength of 2 times the length of the string, a fundamental frequency of the speed or velocity of a wave divided by 2L, and the velocity is found as the square root of the tension divided by the density. Then you have the second and third harmonics pictured here. Second harmonic meaning there are 2 antinodes, and the third harmonic meaning there are 3 antinodes. And you find the wavelength of the nth harmonic by taking 2L divided by n. And the frequency of the nth harmonic would be n times the fundamental. And n would be any number 1, 2, 3, 4, so on. Any whole number integer. Okay, so that was stuff that we learned back in chapter 11. Now, we are looking at standing waves within a tube. We ended last video looking at the first 3 harmonics. You have your fundamental frequency. Then you have your first overtone, also known as the second harmonic. And you have your third harmonic, second overtone, also known as the third harmonic. An overtone is basically just any possible harmonics above the fundamental frequency. That'll become important in just a moment. So this is your fundamental. This is your first overtone. And this would be your second overtone. And what we saw at the end of the last video was that the length of the tube was equal to half of a wavelength for the fundamental frequency. The length of the tube was equal to the wavelength of your second harmonic. And the length of the tube was equal to 1.5 times the wavelength of the third harmonic. Hopefully you've started to see the pattern already, but what it turns out to be is that the wavelength of the nth harmonic would be 2L over n. The frequency of the nth harmonic would be n times the fundamental frequency, and n equals 1, 2, 3, 4, so on, any whole number integer. Notice that those are exactly the same equations that we had for the string. So the equations for the string and for the open tube are exactly the same. Now you have another option, which is what we call a closed tube, which is open at one end but closed at the other end. A good example of this would be an organ pipe, but you can also have, say, like a clarinet. A clarinet would be another instrument where it's open on one end but closed on the other end. Now, what happens here is you have a lot of displacement at the open end, but because the other end is closed, you get 0 displacement there. So you end up with an antinode at the opening and a node at the closed end. So this here is only a quarter of a wavelength. So the length of the tube is only a quarter of a wavelength. The next possible harmonic would be this case. In other words, the next possible harmonic, which we would call the first overtone, would be this case here, where you start at a crest, you go down to a trough, and then you come halfway back up again. That's more than half a wavelength. It's less than a whole wavelength. That is 3/4 of a wavelength right there. The next possible harmonic, so we'll call that the second overtone, is the case where you have an antinode goes to a crest, goes to a trough, goes to a crest, and then back to a node at the end. So you have one full wavelength here, plus you have another quarter of a wavelength that you go back down to the node. So that's 5/4 of a wavelength. So notice those equations then. The wavelength of your fundamental would be 4 times the length of your string. The wavelength here would equal 4L divided by 3, and the wavelength here would be 4L divided by 5. So if we follow the same pattern that we did before, you see 4L over 1, 4L over 3, 4L over 5. So that 3 and that 5, those are the numbers that we're going to go by. We're going to call those lambda 3, lambda 5. And it turns out then that the wavelength of the nth harmonic will be 4L over n. But notice that there is no second harmonic, there's no fourth harmonic, there won't be a sixth or eighth or 10th harmonic. N has to be an odd number. So if we go through the whole process like we did before, we end up getting that the wavelength of the nth harmonic is 4L over n, and the frequency of the nth harmonic would be n times the fundamental frequency, but n can only be odd numbers. This is the difference between harmonics and overtones. Here you have the first harmonic, third harmonic, fifth harmonic. There's no such thing as a second, fourth, or sixth harmonic. And yet we still have, this is our fundamental frequency. The first possible harmonic above the fundamental is the third harmonic, so that our first overtone is n equals 3. And our second overtone is n equals 5.